wasn't Dark Souls.
No.
Keeping Dragon. Starts with Glenn.
He's like, yeah.
But it's like, it's like
Oh man, that's
some
so
chemical
You're right, let's go. Good job. They just pass up on the Challenger Series every time because you know
They just want to prove
what happens. Diseases.
yeah. Like, it's just like transport.
Just
Okay, everyone, let's go ahead and get started. Wow, much better than No Show Friday. Looks like I doubled my attendance record on this Monday. So, what to talk about? My leg's better. My kidney's still pretty bad. I had to lock her in the bathroom because she's become such a behavior problem. She had to do that. If the cat really gets a behavior problem, you basically have to do like this. You clean the bathroom, you put them in there, and it's like a timeout. Then I have to put her in there for like a couple of days, and she's not going to learn otherwise to behave herself. So, anyway, not your problem. Let's see, where are we at? Got to finish up this whole multi-component phase diagram stuff. And I'm tempted to try to finish it there and just stop, so maybe we'll leave early. Wednesday I'll have your last set of homeworks, and that will be it. I have not posted an 11th fake homework because there really is no point. I mean, this stuff is so damn easy. I mean, I can't even come up with anything. As I warned you on the test, I'll have something mostly from last lecture, maybe a little bit from today's lecture, maybe a little combination of both, which will make sense when I get to the lecture. And then, let's see, Wednesday we have a review, Friday we have the test, and then we have 2 lectures. Again, I'm probably going to go over topology, probably, or maybe I'll do it today, depending on how far I get. And then we have a review on the following Friday, which is going to be kind of rough, all right? So that's going to be me barking continuously for 2 straight hours. Easy for you, hard for me. Maybe I'll have some little joke I'll tell, I don't know. Anyway, and then after that, now the final, now one of you emailed me, and I think you're wrong. One of you thought that the final is 8 o'clock Monday. No, Wednesday 1? No, Wednesday 12. Is that right? Have any of you looked this up? No, it's Wednesday at 1. Wednesday at 1. I'm pretty sure about that. So anyway, look it up. It's online. I don't know why UIC, they always wait to publish their final exam schedule. I don't know why they do that. I mean, they know ahead of time when they're going to do it.
But it's been out for a long time, hasn't it? It's been there for a long time.
Monday 8? No, I don't think so. I'm pretty sure that's wrong. No, look it up. We gotta look at, I mean, I have to know this, all right? No, seriously, it's on the UIC website.
It says on the website, Monday 8 a.m.
I think you're misreading it. No, so you have to look at the left-hand column and look at the 2 o'clock. No, 2 to 3. 2 to 3? No, we're 2 to 3. 3 to 4, that's right, 3 to 4. I was thinking about Friday.
So Monday 8 to 10.
Seriously? Monday 8 to 10?
4. Wednesday 1 to 3 is 2 to 3. For people who are 2 to 3. So you check 2 to 3. That's Wednesday.
Because I had the L wrong.
Yeah.
Okay, so 8 o'clock Monday.
Yeah, that's
Well, I'm glad I don't have to
to take the test. Okay, calm down, folks. All right, so let me double check that. Okay, but so it sounds like it's Monday, 8 o'clock. All right. Really? It is Monday, 8?
I wish it wasn't. That's like...
What can I do, folks? I swear to God, I'd rather do it at a different time. Actually, here's a little story.
How many of you had Audrey? How many of you had Audrey for freshman? Yeah, about a third of you, which is about right. She actually used to give her tests at a different time so that she could give you extra time. And guess what happened? You guys are not with some dick busted her on this because she's not supposed to do it. And then she wasn't allowed to do it anymore, so then she had to restrict the hours that she did it. I mean, talk about shooting yourself in the freaking foot. I mean, why would any idiot do that? But anyway, that's what happened. That's why Audrey had to stop giving her exams at night because she wasn't technically supposed to do it, even though she was doing it in your favor. So I forgot why I brought that up. But anyway, okay. Monday at 8. Sorry, guys. Now, some of you emailed me, said that you have conflicts. By the way conflicts worked is, if you have like 3 or 4 exams in a single day, it's based alphabetically, and I don't know which way we're going this year. Every year they flip it. So in other words, if we're going down the alphabet, I take precedence, meaning you can't change my schedule, or if it's flipped, then I have to change your exam. And I'll get you a second final exam, which is not the best option, but we live with what we have, right? So anyway, actually it was kind of funny when I was an undergrad at the University of North Carolina. What they had this gigantic supercomputer. I'm not kidding you. They had a supercomputer calculate times for finals such that no one had a final at the same time or more than 2 finals a day, and it worked. It worked perfectly. And here we just have that half-assed website that you see. So anyway. Can't get in trouble for saying that. Okay, so anyway, so again, tomorrow is a review, and Friday is a test, and then we have 2 more lectures, a review, and then Wednesday at 1, no, just kidding, Monday at 8, we have the final. I don't know if there's much else to say. Do any of you have any questions, or are we okay? We're set? Now that I have some idea what the hell I'm doing, which is kind of good. We're set? Okay, all right, so anyway, I know everyone, I know you're a little anxious. I know it's the end of the semester, you're almost done. We only really have 2 more classes left. Don't forget that if you don't ignore this last test. Yes, it's very easy material, but if you ignore it, you're not going to do well, which is what happens every year. Okay, so pretty please, with sugar on top, study for this last test. And don't forget your final. Right? Come on, I see you guys right there. Point right at you. All right, so multi-component phase diagrams. So remember, there's 2 flavors. There's pressure versus composition, which is what we started out with, and that's when we got some of the basics of like here. You know that at low pressure this would be the vapor, and this would be the liquid. And but the main thing is that the reason that this is so damn easy, which is nice, in all honesty, is all right, so I'm going to have, I already promised you a life, universe, and everything question, and what I'm going to ask you to do is just mentally walk through it, right? So here, this is at low pressure, that means that this is the vapor, this is high pressure, that's obviously the liquid, and so I use letters. Now I'm not going to require you to remember that Y means gas phase. Whatever, I don't care. If you get that wrong, it doesn't matter. And that this would then be the liquid line, so that makes it a chi. And I'll have these lined up with tick marks. Again, I'll be very careful with that. It'll be obvious, and if you just completely screw it up, I'll count it right, doesn't matter. And so then that's what we did on, Wednesday. And then on Friday, what we did are much more interesting. We did the same thing as a function of temperature, which is kind of more relevant. And that's the thing I'm going to probably put on the test. And God knows we did several different flavors. We did liquid, we did liquid vapor. And then right towards the end, I kind of ran out of time. We started combining the 2. And also remember that, so these were non-ideal situations. Now in pressure, right, this is Reagan's law. So this is, that is for an ideal solution. And then the thing I like about temperature versus composition, again, I'll stick with the letter A, whatever. We can we can introduce non-idealities, because remember, ideally, all things mix, but things aren't ideal. And so we can have this kind of behavior, all right? And so this would be two liquids. And I have to feed you a little bit, right? Because you saw that there was all kinds of behavior last time. We talked about how we can have two liquid behavior like this. That depends on delta S. That's unusual. Normally things work like this, so this is a two liquid behavior. And then, since this is already a non-ideal solution, I'm definitely going to have, I'm definitely walking into an azeotropic situation, which works like this. There we go. So we did. Right up here. Okay, so what have I done? All right, on the test, I've said this is a liquid-liquid vapor diagram. That's what I fed you. Now, again, recognizing that this is most likely two liquid behavior, because most liquids tend to mix when they're warmed, which makes a lot of sense. So that makes us the one, so this makes the one liquid behavior. And then at high temperature, I know that this is the vapor, and then this is the vapor liquid. So this is what I've asked you to do on the test. So already you've got about 70%, so that's a C. And then I'm going to have on here, I'm going to have little X's. I'm going to say, okay, I've got a liquid, and I'm slowly increasing the temperature. And I want you to tell me what's there. Okay, so I can easily see a 10-point question right here. And here, you know that, sorry, didn't label it right. So here's liquid 1. Liquid 1, here's liquid 2. And, okay, so the liquids mix. Again, do not do this. That doesn't make sense. This is one liquid phase, and it has this composition. Looks like about 60%. I don't know. Again, I'll make the tick marks add up. Okay, I heat it up more. And now I've got a vapor liquid. And again, I have to figure out what's what. I see that this is the liquid line. And, okay, so it lines up there. Just randomly did that on purpose anyway. And then this is the vapor. So that is actually technically a line, and I don't really care about that. And then you go up here, and what most people do, if you're going to miss some points, which you shouldn't because this is too easy, some of you go da-da-da-da-da, bad. Right, don't do that. This is one vapor, and remember there's no such thing as multiple vapor phases. That's like ridiculous. So, anyway. So anyway, something like this will be on the test. And just walk yourself through it. And also, let's see, what else can I ask? Is this two liquids that like each other or hate each other? Remember, this is non-ideal, and that means that ideality means that A and B have different interactions than AA and BB. Now, I'm asking, does A and B like each other, or do they hate each other? Hate, right? Because, and I'm going to ask why, because the temperature of the boiling temperature has gone down. That means they want to get away from each other, which means they go into vapor phase, because vapor phase things don't mix. And there you go. Okay, now here's the thing. I got 10 more of these. And again, I don't really care about the specifics of any individual phase diagram, is that you walk through it in here. You walk through it in here, and you're going to be fine on the test. Okay, so here's another thing that can happen, is that these can touch each other. Here, let me just draw it. What does that look like? God, no, I really can't label. I really can't even label the x-axis in these cases. I have to just put compositions. That's what I did last time. So compositions of a bunch of stuff. So I have this behavior, I do my two liquid behavior. So I'll write that into liquids. Okay, that's what that means. And then I can do this. It looks like Mickey Mouse, essentially. And these are realistic, by the way. The things actually do this. Again, looks like the top of Mickey Mouse. Again, I have to just walk myself through it. Two liquids, it's obvious. This is going to be a liquid vapor. This would be a vapor. This is going to be a liquid vapor. And this will be one liquid. Okay, so there you go. So here, let me get into my points. As I raise temperature, what have we got? I got my two liquid phases. Again, mostly B here. on the left and on the right, mostly A, which kind of makes a lot of sense, but then I heated it up. And then I have one liquid phase with that composition. I then have my liquid vapor, and this would be the vapor phase composition. And this would be the liquid, sorry, it gets messy, right? You know that. This would be the liquid phase composition. And then I heat it up here, and that's my vapor phase composition. So I boiled it. So there you go. Okay, liquid vapor. Something like this on the test, all right? There's others. There's a question.
Yes, so if you're in the two liquids curve, how do you know which one is liquid 1 and which one's liquid 2?
Oh, doesn't matter.
Okay.
Right. Now, again, in terms of the test, I'm really careful about this. I have, I always do this with Adobe Illustrator, and I have like literally a ruler tool that allows me to line everything up so that it'll be a guide for you. Like this will be 0.1 and this will be like 0.9. And when you see that they line up perfectly, that's a hint. You know, you're doing it right. So
Okay.
yeah, so look for that. Yeah, but I'm not gonna screw that up.
Okay. I was going to say, on the exam, we could say the composition of the two liquids is 0.1 and 0.9.
Yeah, that would be fine. Oh yeah, absolutely. The main thing is, so what did you do right? You answered that there's two liquids. So there you go, and that's really all the question there is.
Okay.
Okay, so liquids, vapors, solids. Let's do liquid, solid. Okay, so liquid, solid. It sucks. Anyway, okay, so liquid, solid. Now this is very different. Okay, again, I'm going to use the function of temperature, which is kind of the only thing that matters. Again, I don't have quite the weirdness in terms of these chi's chi's or y's. I just like chi's. That'll be chi A, goes to 1. And I said this a long time ago that twice this would come up, that solids have activities of 1.0. And that means that they're pure in their own right. And here, let me finish it. So again, this is solid liquid. Again, I have to give you that information. It's impossible for me not to. Sorry, that should go further up. And again, I have to think about what's what. And I know that if I have a low temperature, so again, I said this is solid liquid, low temperature. This is the solid. That makes that high temperature. I know my solids will melt. And again, remember, there are two things here, and that makes this the liquid solid. So generally, I put these on the left, and then I'll have my little points on the right. And again, I'm putting it below where the little curve goes to kind of mess with you. Okay, again, I told you this, I've drawn this. You told me this, this, and this, which is sensible. I've got 0.1, 2, 3, and I'm asking you what's there. Okay, so here you've got, you've got two solids. What does that mean, two solids? A lot of minerals do this. God, I can't think of an example off the top of my head, which is kind of bad, but anyway, so I'm not perfect. But it turns out that lots of times you want to make an alloy out of two metals, and you can't. So what you do is you melt two metals, you put them in the same pot, you cool it. Right, so you start up here and you work down there. And for the longest time, up until really about 1900, people thought that they were legitimately making new metals, new solids, new alloys, and they weren't. What happened was people invented the microscope. And when they invented the microscope, especially a polarization microscope, people saw what was happening was that they were getting, when the metal melts, you get these domains of like, I don't know, iron and zinc. I'm just making that up. But anyway, so you try to make a new alloy by mixing these two metals in a crucible, you cool it down, it looks like it's a new material with different properties. It's not. It's just the sum of two different metals. And again, you see this little crystal, and the crystal is whatever the crystal shape is, and that's iron, and then you look right next to it, you see another crystal, and that's zinc, and then you look next to that, it's iron, and it's zinc. So anyway, they didn't actually mix, they didn't react, they didn't do shit, really. You just made a bloody mess. All right, so that's what's happening here. Okay, now here, again, all right, so you say that I have microdomains of one metal and microdomains of the different metals. And that actually is very close to reality. All right, so now we heated it up, and we're here. Now, what this says is that actually in this liquid mix, looks like A precipitated. That's what this means. On the right, A has precipitated, and it's puree. But then on the liquid side, and whatever liquid zone you have this composition of A, and one instead of B. And then you go up here, and again, if you want to screw up and use points, you draw lines to the left and right, which would be wrong. Instead, you do nothing. You do nothing, and you say that there's one liquid phase composed of that much of A and one line instead of B. And again, it will line up on the tick mark, and that's a hint that you're doing it right. So, anyway, hopefully you're not falling asleep. There's one neat thing about these solid phase diagrams, and let me draw a new one. So I don't want you writing over your own notes because that gets confusing. Temperature. I'm just going to recreate that for a very specific reason. This is actually pretty interesting how this works. One saving grace we have. All right, so lead and tin. Jesus, what am I, an idiot? Lead and tin. This is a very good example. And I think you know what that is, engineers. Lead and tin. Begins with an S. Solder. Right, solder. So what you do is you melt something into a liquid state. Again, lead and tin. And what you do is as you drop the temperature, you're going to generate some solid, I don't know, maybe this will be lead, and you have a little bit of a liquid, and what you do is you pour the liquid off. And then the liquid cools, it's like a distillation, right? The liquid cools, and then you're here. And then there's some more solid lead, and then you cool it, and there's some more solid lead, but again, you pour it off, or you pull it out, and you keep going down until you're here. And here is a God, my spelling is so bad. Let me make sure sorry, my spelling really is that bad. Okay, syntactic point. So what you have is, again, all right, so I've asked you on the test, and I've given you a solid liquid phase diagram, and you've labeled this. This is the melting point of B, and this is, I never planned ahead. This is the melting point of A, and X is again the eutectic. I'm just writing it because I haven't spelled it before. That's the eutectic point, and the importance of the eutectic point is that the solids, the two solids in their weird mixed state, melt at a lower temperature, and this can actually really be extremely substantial. So not only do you see that from the phase diagram, this A and B melt at much higher temperature. You see how coherent as well. It's like a distillation, kind of except for solids, which is weird, but anyway. And so solder definitely melts at a significantly lower temperature than lead or what is it again? Lead and tin. Sorry. But the damnedest thing is, it's kind of always bothered me, is that lead is not really that toxic. So lead is actually a fairly abundant mineral element in our Earth's crust. It's kind of everywhere, and it has a really bad name because it makes little kids stupid. You know, if you put it in paint, the paint lasts a long time, but little kids, I never ate the lead paint, but sounds funny, doesn't it? I'm told that it does. Little kids do find it kind of tasty. It has a bit of a pastry taste, apparently. Again, I wouldn't know. And so, seriously don't know, and I wouldn't be here. But so little kids started eating lead. This is like when I was like 10 years old or so, and everyone decided that lead was the boogeyman. It was because children got hurt. And that's actually true of a lot of chemicals that are considered toxic, like cadmium, lead, mercury a little bit, not quite so much. It's not because of the toxicity, it's because there was an accident with it. In other words, it was easy for someone to get poisoned by it, not that it was necessarily poisonous to begin with, right? H2O is technically the most poisonous thing on our planet because lots of people are drowned. So, so lead is considered a boogeyman. It's because it hurt children, and we are very prone to not letting children get hurt. But itself, it's not that bad. Now, if you're grown up, it really can't hurt you. I mean, you have to inject lead into your blood before lead can really hurt you once you're grown up. So, anyway, just a little stupid thing that all us students are kind of true. It's kind of one of the very stupid things. Anyway, all right, last bit, and let's see whether we get to symmetry or not. Reactive or unstable systems. Or unstable. Okay, so this is kind of like what we did Gibbs phase rule for reactive systems. This is kind of similar to that, except it's kind of easier actually. And let's talk about, let's do reactive. A plus B equals A. And by the way, this is a solid-solid type of situation. And my favorite example is actually gallium arsenide. So gallium is a metal, arsenic is kind of a metal, not really. It's considered a semi-metal. Gallium has an orthorhombic type of crystal structure. So it's a screwed up square. That's what orthorhombic is. Arsenic is rhombohedral, which is a really screwed up square. And then if you have gallium arsenide, what you have is a zinc blende, which is kind of like NaCl. So my point is that if you really reacted, if A and B had really reacted, you can tell. It has very different properties than either by themselves. It's like gallium is a metal, arsenic is a shitty metal, that's one way to put it, and gallium arsenide is a semiconductor with a band gap, which is significantly higher than that of gallium or arsenic. And okay, so anyway, let me draw the phase diagram for that sucker. And I'm a little tempted to put like that SOB there on the test, but if not, I'm going to put this one. I haven't decided yet. I haven't really started working on it. Sorry, I know I should have done this later. Okay, so again, I've got my solid type of phase diagram like that. And what I've got is my liquid solid, kind of like that. And here's how this is different, right here. And this is at 50%. Here, again, I'm not even sure how to label the axes, because it does really get pretty confusing. I can't write that today. Okay, so again, I have to figure out, so I've told you that this is a reactive, solid, liquid phase diagram. So you do this, you do solid, liquid because it's hot, and you do solid, liquid. Okay, so that's 3 points, no problem. You have 10 points. You got 3 of them. I've drawn point 1, point 2, point 3. Okay, excuse me, 3 more points. What's what? Okay, as usual. So line left, well, yeah, again, the only hard part. When you want to draw lines of that, what do I know? Well, that's why I have class, all right? Okay, left, right. In this case, you have left and right. You did before as well. In here, you've got gallium arsenide, again, which is a very different material than gallium or arsenic by itself, and it looks like you have excess gallium. Sorry, must be perfect. Anyway, so you have metallic gallium that's just kind of floating at the bottom. Or sorry, it's like ingrained with gallium arsenide. Okay, so that was easy. You go up, and I've taken this melt of 2 different metals. One's a semiconductor, one is gallium, apparently, according to the way I've drawn it. And I've got solid gallium arsenide, again, the semiconductor, which is actually kind of a blue color. And then I've got a liquid, which with this composition, so I'll call that isotate. Gallium, I guess, the way I labeled it. And there you go. And then I go up here, and again, I'll put the drawing thing. That's straight, kind of straight. And again, do not do that, do not do that. Hard part, watch the videos, anyway, watch Monday. sorry, watch Fridays, watch Tuesdays, and that should do it. I don't go left or right, I just recognize that that is the liquid solutions composition. Again, don't forget that the alum and arsenic are very different on their own right, so. Got a couple more of these, I know this is probably driving you nuts. Okay, here's another one. A and B is unstable. Again, this is true of really like a lot of stuff. And I can't think of an example off the top of my head. I know a lot about random chemicals, but okay, so again, temperature versus composition is by far more interesting than pressure. Especially when I'm doing, I'm doing solids. I mean, am I going to pressurize a solid? What the hell does that mean? Of course I'm going to heat a solid. So that's why temperature versus composition and more concrete. A and B, something like that. Okay, so if A and B is unstable, what I'm going to do is I'm going to have same type of solid, and I've got my AB, and that looks like 50-50, so it's kind of like gallium arsenide, but why is it different? It's like this. All right, notice that it's not symmetric. That's essentially what I've done. I've not drawn a symmetric phase diagram. So what happens is, and if I put one of these on the test, it would probably be this one. I don't know that, not promising, all right? All right, again, what have I done? I've given you this. This is all I gave you. That, I said, it's a solid liquid. You write solid, because that's, you have solids at low temperature. You have a liquid at high temperature. That moves in between solid and liquid, obviously. Again, just walk your way through it. Now I've given you points 1, 2, 3. Here, I've got AB. I've got AB looks like, oh, what else have I asked? How much more AB do you have versus B? Sorry, A. Okay. You have more AB or A? Which is it?
A.
AB? You said that because you heard him say it. You have more AB. Remember, guys, don't forget this, right? This stuff is really easy. I'm sorry I haven't had a homework, but it's just so freaking easy, all right? Remember, where the point is closest to, by the lever rule, is what you have the dominant phase of. So if you have a dominant AB, here, let me label that. It doesn't seem to AB. Okay, the point's closest to AB, that means you have most of it there. Then I've got some A, and I've got a liquid composed of A and B, but it's not chemically distinct. It's not behaving itself differently. It's not behaving itself differently, like in the case of gallium arsenide, where I even had a different crystal structure, which was very different. And then here I've got a liquid. Bad kitty. No, just stay right there. Stay right there. One liquid with that composition question.
Would you need to make any calculations with the liver rule, or just qualitatively say?
Oh, well, I mean, you could technically, pull out a ruler and figure out, like what percent. That's going to be qualitative. Did I just say that? No. Anyway, yeah, it's all kind of qualitative, so I don't really, yeah, I'm just going to ask, what do I have more of? And I kind of like this stuff a little bit more. So I'm going to be like, does it like each other? How is the solution not ideal? Yeah, I guess I can ask, do I have more vapor or liquid? Yeah. Again, I feel bad about not putting up a homework set, but it's just so freaking trivial to do this. Same time, guys, do study, do watch the video, because there's really not a lot else I can do. With this, if you don't study it at all, even though this stuff is very simple, you're going to miss it, right? So, anyway. Okay, well, I do have a ton of time left, so let me get into symmetry and topology of molecules. Okay, don't go nuts on me, all right? Cutting the test off now, all right? But it may be on the final. In fact, it will be on the final because I'm making you sit here. All right, so the next information, again, I've cut off test 3 now. But I'm going to ask one question based on today's lecture. Again, Wednesday is a review. Then I got Monday, Wednesday, again on topology of molecules. And I'll put one question on the final. All right, so don't fall asleep, don't ignore this. This is easy. Now remember, this is Chem 444. And again, God, folks, if you could, I know this isn't going to happen, I know it's impossible, but if 10 of you could write to last week at our department head, Luke Hanley, and say you're going to take Chem 444, you might bring it back. If you could do that, I know that's just not reasonable. Engineers don't do it. You've got engineering stuff to do, okay? So it'd be great if you could do it, though. And there's one thing, I'm really proud of this university because we do teach more. We teach 15 weeks as opposed to 13 weeks. We had PChem being a 3-course thing as opposed to 2. So you have gotten all the content that the Northwestern and University of Chicago kids have got. You got exactly the same stuff, plus a little bit more, which is awesome. That's how you compete against the rich kids. You know, you would have to be better than them because they got all the money and so money talks, right? So again, so I'm going to cut off the test here, but let me go over some Chem 444 stuff, and that is to understand again topology of molecules. And let me start with just some examples. And this is one of the really bigger deals of physical chemistry, is understanding shape. And so iron, let's take iron. Iron likes to form, well, it's a planar. It likes to form a planar ligand sphere. And so a lot of things about iron and everything else in this world can be understood from its shape alone. And shape is very qualitative, right? I understand shapes. A 5-year-old understands shapes, but you can get a hell of a lot out of the molecule based on its shape. Even if its ligands are all crazy like that. Oh, and this one would be the same, right? So it's got some. Yeah. Now it turns out that a lot about this molecule can be known by the fact that it's a flat plane. I can calculate the number of vibrational spectrum I should be able to see. I can tell you whether in 346, should I even bother to do this integral? You know, again, quantum mechanics, integral, and some of them you don't need to do because of the symmetry, because it's flat. Some of them are going to be 0. And you know that, again, because of the shape. And I know that really quite well because this is what I do for a living. So, what else was I thinking about symmetry? Even though, you know, the excess is floppy and messy, in its local environment, it's flat. And again, that tells you often whether you even really want to do quantum mechanics on a molecule, or whether you need to or you don't need to. And that's basically about as far as I'm going to get. And you're not going to get that 346. Robert might introduce a little bit of it, but anyway, it is what it is. Okay, so to understand symmetry and spectroscopy, especially when you do the spectroscopy component, so hopefully Robert will clear that up. You have to understand what an operation is. So we have symmetry operations. Symmetry operations. Okay, now based on the number of symmetry operations, I can define how symmetrical a molecule is. And if a molecule has no symmetry whatsoever, I learn a lot about it. That's actually like really kind of important whether a molecule is symmetric or not. Especially, how much more time? I got plenty of time. Okay, this is a bit of an aside, so don't even write this down, all right? So as I've drawn a couple of times, I have this energy versus like a coordinate, like this is a vibrational coordinate. For example, I've shown you this a couple of times when we talked about degrees of freedom. And I've shown you that there were vibrational energy levels. And I told you that molecules do this. They have to move a little bit, just how it is. And if they absorb energy, then they do this. If they absorb more energy, then they do that. I can go faster than that. But nothing in between. And here's the damnedest thing. Let me draw it this way. There may be sublevels within those levels. That would be I'm vibrating this way versus I'm vibrating that way versus I'm vibrating that way. That works, that totally works. But it implies shape. It implies that a certain shape exists if you have those degeneracies. If there's no shape to the molecule, it's not on the table. They don't exist. If the molecule has a lot of symmetry, if it has a lot of symmetry, then a bunch of sublevels exist. It depends on the shape. And that's pretty useful to know. And so that you can look at spectra and kind of interpret that. That's going to be relevant to 343 as well. Okay, so let me go over different symmetry operations you can have. All right, one is E. And this is very simple. It's a bunch of letters. And E means do nothing. Okay, and that's important for weird reasons. That's when, okay, so a symmetry operation is like I'm going to rotate it, does it look the same? I'm going to cut it in two, does it look the same? I'm going to rotate it and flip it and then do a mirror inversion, does it look the same? And E is do nothing. Okay, now what else have I got? I've got this guy. This is a mirror symmetry. Okay, mirror symmetry. Now in this case, that's this. Sorry that my drawing is pretty bad, but anyway. Okay, I see a mirror plane there, and I see another mirror plane. Right there. Okay, I see. It's okay if you don't draw that. I mean, it's very simple. Oh, here, I've got a better example. So hopefully you see that. Let me draw something that all of you can copy and digest. Let's do H2O. Okay, now nothing is coming out again. So I've got one mirror plane here, which contains the molecule. So I'll call that a sigma to sigma V. The V doesn't mean anything. The reason there's a little V there is because there's another symmetry plane, which goes like this. So I'll do that. So sigma V prime. Just they add the little V and the little prime just so you know the difference between the two. And this guy usually contains the molecule, and that one bisects the molecule. There's a little prime. It doesn't really matter. It's not very much on that. But anyway. Okay, mirror symmetry. So again, I can see that when it comes to quantum mechanics, I can see that this sucker and this sucker locally are going to have degeneracies when it comes to whatever quantum mechanical calculation I'm trying to do. And let me also give you another bigger picture thing, especially when you're, are you all in 343 next semester? Yeah, just about every one of you are in 343. There is a big spectroscopy component, and you're going to be doing Raman and infrared, and whether something has vibrational stuff appearing in the Raman and infrared spectra depends exactly on its shape, whether it has these degeneracies and yada, yada, yada. Okay, anyway, there's this guy too. C hat. This is rotation. Rotation of 2 pi, oops, sorry, it should be 2 pi over n. So if n is 1, it means I can rotate it 2 pi. Remember that's 360 degrees, which is nothing. And notice that C1 is the same as E. It doesn't do anything, does it? If I rotate something 180 degrees, no, 360, God, what's wrong with me? If I rotate something 360, it's the same thing as doing nothing. So now you're starting to see that, what if I did this twice? What if I did 2 symmetry inversions? Then that's the same thing, as E. Right? So these things can actually play on each other, and that's part of quantum mechanics that's coming up, so just look forward to that. Let's see here now. Here's a good example. Boron always coordinates to 3 things. And let me do that. F1, so let's do boron trifluoride. And 3, and 2. And if I do a 2 pi, OCD 2 5/3. And then that goes to, so turn once, which is kind of obvious. Okay, there you go. Now, again, I know it's not, I know it kind of doesn't mean a lot to you right now, but it will next Monday, that I can do these operations kind of over and over again. And the more I can do them, the more symmetry is there, and the more my quantum mechanics is affected. And again, I'm not going to be able to get to that till Monday, so you're just going to have to trust me here. And notice what I can do is, here's my designation for that. Let's say, let me do an aside here. Let's think of this guy here. Right, that's a good example. So this guy has local symmetry, and that's C4 symmetry. So here, I'll just draw that again. And again, this is, let's forget about the extra ligands. Sorry, I should have had a better example. I'm sorry, I screwed up. Anyway, all right, so square planar, and it has fourfold symmetry. So I can see that this has C4 symmetry. Now the thing is, I can turn it once, twice, 3, 4. If I turn it 4 times, that would be this. And if I do that 4 times, I haven't changed anything. Right? So you see, I'm actually multiplying. I've done C4 times C4 times C4 times C4. That's what I'm doing when I say this. Now notice that I also can do this. C4, let's do that 3 times, and let's do it one more time. See, what I'm doing is I'm building up a multiplication table. And that means that C4, the -1 times C4 is nothing, right? 1/2 times 2 is 1. That's what I've done. Sorry. 1/4 times 4 is the number 1. That's what I've done. Mathematically, it's all the same thing, except it's shockingly easy, right? I mean, I think a 4-year-old can take 1/4 times 4 and get the number 1. And you're doing that with shape. And again, it's going to affect 343 stuff and 346. Here's well, I need to end there. Let me just do two more. Again, I introduce these symmetry elements. Let me do 2 more. Right? Chopping up a bit. Let me do 2 more. And understand that there's these symmetry elements. I'll just start from the bottom. Understand that there's certain symmetry elements and that they can be multiplied, which is the same thing as acting on the molecule once then twice. And if that is meaningful, then it's meaningful. It's basically what it comes down to. Let's do I. Okay, that's inversion. Inversion works like this. This is actually a molecule this is my first molecule I wrote the first paper on. It's a carbonyl. So it's like our iron guy, except that it has, oh God, sorry. Except for this, let's see, this is 1, 2, 3, 4, 5, 6. You can see that these guys are in a plane. Hopefully my drawing isn't too bad. Anyway, you can see that these guys are in a plane, and these guys are equatorial. Doesn't look so good, but anyway. And then upon inversion, this is how you do this. You say, what happens when I do the symmetry element? You see that, let's see, 1, 2, 3, 4. Okay, this is the 2 over here. CO, this is CO1, this is CO3, this is CO4. Again, don't save that for stoichiometry, all right? And then this is number 2. And this guy is, sorry, again, it goes to be CO4, CO6, and this is CO5. Okay, so that's an inversion. And last bit is an S. This is improper rotation. Okay, again, the name of the game is what can I do to spin, flip, rotate, invert, mirror image this molecule? How many things can I do? And that's important, which you'll see on Monday. This is rotation. Plus mirror image. Sorry, my use of the word is really bad. Mirror image that's perpendicular. So that's what that means. Let me show you what that is. And then we'll break, and then we'll have the review on Wednesday. We'll have the test, and we'll have the A's. We'll have the study. Let's do this guy. All right, so I've got this. Okay, so this is like Allen or something. I don't quite remember. Okay, now the way improper rotation works, I see that I have a OCD. So I'm trying to draw an S4 symmetry element. So what I'm going to do is rotate this just by 1/4, and that gives me, sorry, I'm not really drawing this very well. So I've done this. So this guy's now on top, this guy is now on the bottom, and that means that this guy is now sticking up towards me. Make sure I'm drawing that right. Okay, this is the best looking drawing I can do. All right, then I'm going to reflect it this way towards that. Right, that's the second operation in the symmetry group, and then see that guy goes here, and this guy comes there. Let's see, this guy shoots over here, and that one shoots over there. Which is the same thing as that. There you go. Okay, hopefully you see that, right? Just kick and then okay, anyway, I know this doesn't make a lot of sense right now, but I promise on Monday it will. Sorry, if you look at your test, you do well. See how it goes.
Oh, geez, I went way over, didn't I? Yikes.